Hi everyone. This is the lab presentation for the final lab of the semester on glacial processes. So in this lab today we're talking about glaciers, and glaciology is the study of ice, including glaciers, as well as more generally snow, because snow forms glaciers. Sea ice, like in the Arctic Circle, Arctic sea ice, and ice sheets, which are basically glaciers on a massive scale over land. Now, glaciology is important because remember, 68% of all of the fresh water on the Earth is stored as ice. That's a lot. If you watch the link to the video that I put on Canvas, uh, that clip shows a piece of ice the size of a skyscraper breaking off and floating into the ocean, and it'll melt. Glaciers often, they all go through a seasonal transition. In summer, ice shrinks as it melts, and in winter, it accumulates again. We'll talk a little bit about the equilibrium process in lab today. But over time, glaciers aren't always in true equilibrium. They have years of positive growth, accumulation, and over time, especially in the last few decades, most glaciers have actually been shrinking. We'll look at that a little bit too with the Wolverine Glacier in Alaska. So how do glaciers actually form though? Because for the most part, glaciers are pretty much solid ice, but they form due to snow that is compressed by the weight of other snowflakes on top. Usually takes about a year. If snow stays for a year, it gets covered up and compressed into firn, which is basically the intermediate stage between the loose, fluffy snow uh, to the compacted ice, which is at the bottom of glaciers, which is often bluish. It has air bubbles, sometimes trapped within. But think of glaciers as a solid chunk of ice. And glaciers are not only important because of the amount of water that they hold, but also how they affect the landscape, especially here in Wisconsin. Wisconsin, as we'll see in a couple slides, has been affected greatly by the most recent glaciation events. And how does that happen? Well, ice, in a massive scale, actually can flow, often due to gravity pulling it down, but with enough compression and so much forces involved, ice can flow over the landscape. And when it does that, obviously there's a huge amount of force exerted just due to the weight of the ice. And it can scrape away rock faces, it can push debris such as plucking or abrasion. And glaciers also transport this material to, they might push them at the edge of the glacier, like in a moraine, or it can accumulate stuff on top of the surface of a glacier, and then when the ice melts, it just drops all of that stuff. And there are particular landscape features that we can still see today. Now that the ice is long gone in Wisconsin, we still see these morphological features on the landscape. And we'll look at those in greater detail for the lab this week. Now, glaciologists study different kinds of glaciers. The ones that are over land and are very expansive, we would call continental glaciers. Like ice sheets, for example, they are vast in size. They're relatively flat. They basically expand out in all directions, covering the entire land. Uh, Throughout history, the climate of Earth has changed. There have been periods of ice ages at which the average global climate was pretty cold, I should say. And there also have been times of warmer climates in which there's much less ice present on the Earth at any given moment. And then the continental glaciers have shrunk. And that's what we see today. Um, about 28,000 years ago, uh, Wisconsin was mostly covered in a sheet of ice. But 11,000 years ago, the ice receded and it was primarily in Canada. So don't worry too much about the specifics there, but understand that the features that we see today on our landscape are affected by the past glaciation events. The two main ice sheets today, present day, are in Antarctica, which is basically the whole continent covered in a massive ice sheet, and the island of Greenland, also mostly covered by a giant sheet of ice. And there's so much ice on these ice sheets in Antarctica and Greenland. If the total amount of water stored in the Greenland ice sheet, if that were to all melt and flow into the ocean, the global ocean sea level would rise by 7 meters. It's over 20 feet. That's a lot. The one covering Antarctica is even greater. If all of that water were to melt and flow into the oceans, well, then oceans would rise by 60 meters. That's crazy. So that gives you maybe a little perspective of just how much water is stored in these ice sheets. They're massive. And in summer, they shrink a little bit. Winter, they accumulate, but for the most part, they go through these cycles of warming and cooling, and especially the one in our Antarctica, the Antarctic ice sheet, it forms because of the seasons and the latitude that it's at. It's a very cold climate. So it makes sense that there's ice all year round. To understand the geomorphology of our state, Wisconsin, you have to talk about glaciers because glaciers formed most of Wisconsin in the most recent Wisconsin glacial episode, the Wisconsin glaciation, up to around 11,000 years ago. At that point in time, the climate of the Earth was much cooler, sea levels were lower, a lot more ice. There was a lot more ice on the land throughout the world, and in the northern hemisphere, there was an ice sheet extending pretty much all across Canada, from Alaska all down into the Midwest, the Great Lakes states, and the New England. Uh, Over time, this glacier advanced and receded, and when that happened, the glacier moved stuff on the surface. It moved sand, silt, clay, boulders. It deposited, of course, water as well. As glaciers melted in summer or as they receded over the years, of course, that water has to go somewhere. And from that melting ice, it created river valleys, flowing water, lakes around the terminal edge of the glacier, the terminus, which is just the southernmost or the end of the glacier. And you'll see this area called the Triflis region that has a different story than the other parts of Wisconsin. The Triflis region is in southwestern Wisconsin. It's about a quarter to a third of Wisconsin in terms of area. And it was not covered by the most recent ice sheet. It was just past the edge. So where that happened, there was a ton of water that was flowing off of the glacier itself that carried with it the loose deposits from Canada and northern Wisconsin that were pushed by the glacier itself. So it looks a little bit different now. the features on the land are more likely due to fluvial geomorphology or carved out by flowing water than by glacial events. Like the rest of Wisconsin, 3/4 to 2/3 of Wisconsin, which was covered by the most recent Wisconsin glaciation event. And in that area of our state, we see glacial features, continental glacial features, like eskers, drumlins, canes, kettles. So how these continental glacial features would form are basically that ice melt and rainfall carried with it large quantities of clay, sand, gravel from the ice melt, from the ice mass itself. Clays could be moved long distances because they would be suspended in that moving water, while sand and gravel didn't move as far. At the edge of the frontal edge of the glacier or the terminus, mounds were called moraines, basically deposits pushed like a bulldozer. And wherever a subglacial tunnel began filling in and collecting stuff with it, as the ice melted, that tunnel would drop straight down full of stuff, and it would create an esker, which is a long, winding feature like a mound on the surface. Here's a good image showing an example of an esker. These are pretty common in Wisconsin, actually. Same as drumlins. Drumlins are smoothed out piles of stuff. They have these basket of egg style shapes with their 2 to 3 times longer in one axis than the width in the other. Drumlins are very common throughout the state as well, but they're a little more smoothed out because they were smoothed by the path of the glacier. There could have been a mound or a large outcropping to begin with, and then when the glacier moved across it, it deposited or smoothed out whatever was already there. Whereas a cane is a bit more abrupt of shape, also very common in the state, especially as you go a little bit toward the central region, maybe around Baraboo. Baraboo, there are a ton of canes. And those are piles of accumulation, basically from debris like clay or gravel, or, whatever particles collected on top of the glacier itself in a little pool of melting water. And then as the ice melted away, that stuff again dropped straight down to form a little mound called a cane. There are also kettles that can form. A kettle is basically, imagine when the glacier is receding, chunks of ice may break off from the terminus edge in form of a calving event, which is basically just a large chunk of ice breaking off and being left on the surface of the land, melts over time. So debris would accumulate around that ice, but not in the center, and it leaves a cup shape or a depression on the surface, which often fills with water, and we have things like kettle lakes that form. Kettles are very common, and if you go around to travel to different state parks in Wisconsin, you have probably heard of Kettle Moraine State Park or State Forest, pretty close to Wisconsin. Glacial features are super common in that area. So now you'll know a little bit about the history and the formation of these features on the surface and why they're due to glaciers and the most recent glaciation event, which ended around 11,000 years ago. If those definitions of glacial features related to continental glaciers are unclear, I encourage you to read this slide and the next on glacier eskers, drumlins. Read up more in your textbook or in the lab document for this week. Okay, so up till now, we were talking about continental glaciers. Now let's shift to alpine glaciers, which go through a slightly different process, but for the most part, the physics of it generally remain the same. That glacial ice, it would flow downhill due to gravity over vast periods of time, and they would influence the rocks and the topsoil and the features that we can still see today, even though those glaciers are mostly gone. Here are images of Yosemite Valley. One of its most striking features, Bridal Veil Falls. To imagine 2 to 3 million years ago, this whole valley here would be covered in ice. It's a lot of ice. That was a time that the climate of the Earth was much cooler. And in the Sierra Nevada mountain range, it was possible for glaciers and a mountain ice field to form. They would go through periods of more ice or less ice depending on the climate. There's a lot of time involved here. But this ice field covered most of Yosemite Valley in the area and sent glaciers down into its valleys, the lower valleys. The glacial ice transported loose rubble, sand, silt, clay, things like that, and scoured out features on the landscape too, including striations where it scratched the rock, or piles of rubble accumulated on the edge, like moraines. But a lot of the debris just flowed downhill in streams that were filled with glacial melt. But we're going to look at greater detail in some of the features that are associated that you can still see with glaciers and how they formed. So we already know that Yosemite was a glaciated landscape, and the landforms that are a result of that include U-shaped valleys, jagged peaks. Like here is not in Yosemite Valley, but the Matterhorn is a great example of an arete, these jagged peaks. And we have these moraines, already mentioned, and waterfalls. Going back to the previous slide, I was talking about Bridal Veil Falls, but why did that form? Well, imagine at one point in time, this valley totally filled up with ice, giant glacier, up to this level, and then this other smaller glacier forming in this little U-shaped valley here at the top of the waterfall. This ice would flow out into and on top of the larger glacier down here, which is why now that the ice is gone, we have this giant waterfall that formed of a U-shaped valley up higher elevation, and then a giant leap down into this much larger, wider U-shaped valley, both formed by glaciers. But you have to imagine the height of the glacier was up here at one point, so it was possible for this ice to float right on top of the other one. So let's go back to other sorts of glacial formations, aretes, horns, cirques. These words, which have their origin in French, actually are carved out by glaciers, so they're erosional. The rock was eroded away by flowing ice to make, so if we imagine two sides of a mountain ridge carved away, that would make an arete, which basically looks like a mountain ridge. Arete comes from the word for to stop, because it's very much like a physical barrier. A mountain ridge, I mean, how are you going to cross that? A horn is basically like the Matterhorn, is a lonely peak that was carved out on 3 or more sides to leave just a singular mountain. Each sides of these would be carved out by glaciers over time. And cirques are concave circular basins. That might be a good mnemonic device to remember. Cirques are circular basins carved out by the base of a glacier as it erodes by flowing downward due to gravity. Moraines, on the other hand, would be depositional, where they deposit stuff. They deposit till often. Let's use that word for the unsorted glacial sediment just deposited further down a glacier's path, like a bulldozer would move debris or stuff like dirt or boulders. It pushes it and deposits on the side or at the terminus of the glacier. Like in this example, this shows really well the different kinds of moraines that might form, whether stuff is deposited on the side of a glacier, like on lateral moraines, or being pushed forward like a recessional or terminal moraine. Terminal moraine just means the furthest that a glacier ever made it and over time. So that's the furthest that the glacier ever was, and it pushed most of the stuff there down to the terminal moraine. But at periods of climate warming and cooling, there may be intermediary moraines like recessional moraines. Still all formed at the end, pushed forward like a bulldozer. Now a saddle forms. A saddle is another glacial feature. A saddle forms sort of like Bridal Veil Falls in that it's like a gap between arêtes carved out by glaciers as they move downward. They gouge out these U-shaped valleys. So to remember a saddle, just think of a U-shaped valley. They may vary in size, but usually a saddle refers to these smaller U-shaped valleys, like at the top of the Bridal Veil Falls in Yosemite versus in the larger U-shaped valley basin at the base of the falls. So think of a saddle as higher up, like a gap on an arête. And of course, as these glaciers carve out, depressions in the valleys, that hole could fill with water. Liquid water may become trapped there and form these lakes. So this is how, in the top right here, this diagram would show how the glacier would move. So it moves downward due to gravity. And as it moves at the steepest path, here at the bottom, it carves away most of the ground and rock, creating these sorts of depressions or cirques. Now, as they get deeper and deeper and the glacier melts away, that is when they fill with water and they become these lakes that we see in present landscape. For example, here on the left, these are called paternoster lakes. The word coming from basically a chain of beads because they are a chain of lakes. Paternoster lakes are a chain. They're multiple lakes that form from different glacial erosion over time, but forming in one chain, versus a tarn lake, which would be like an isolated lake, just one. You can think of a paternoster lakes as a chain of tarns. I'm not going to go into too creative detail. You will see some examples in Google Earth for the lab today for this example for Alpine glacier formations and continental. So that may help you understand what the definitions of these features might be. Now that is the end of the lab presentations for the semester. This is our final lab, Lab 12. It's due on December 19th I strongly encourage you to get that in before then, because that's going to be a hard due date due to the semester ending around that time. So I won't be able to take late assignments for this lab, so be sure to get that in. Now, as a reminder, your lab grades, there have been 12 of them over the semester, um, actually get factored into your final lecture grade. It becomes 35% of your overall lecture Geography 120 grade. If you would like to work on past assignments, please email myself or Ryan, and we can help you work through that. And overall, your effort has been amazing throughout the semester, given the circumstances. Normally, we would be able to meet in person in the lab room in Bolton Hall, but we did the best that we can, and I thank you sincerely for the good effort that you have put in. Now, without further ado, I will end the presentation here. Good luck with Lab 12. Please, again, email us if you run into any confusing material, or you would like some help with the assignment. And have a nice and cozy winter break.